Have you ever heard that the average person swallows 8 spiders per year in their sleep? If you haven't, don't worry, because it's not true. That number is actually more like 0 in a lifetime. Spiders won't intentionally crawl into a bed because there's no prey for them to eat there. And in fact, they're likely to try to avoid humans because a heartbeat, breathing, and snoring cause vibrations that scare them away. But this urban legend is just believable enough that it keeps being spread despite the lack of evidence. It doesn't take a lot to spread misinformation. Having data and a visualization to back up a claim can make it even more believable, even if it's incorrect to begin with. This is one of many things you should be careful with when making a data visualization. People tend to think that data visualizations are just a straightforward presentation of data, which by definition is true and unbiased fact. That's not actually the case. If your data set is the color of each piece of candy in this bowl, it's pretty easy to take both the data and the visualization at face value as factual. While it's possible that someone might accidentally mislabel one of the colors, it's quite unlikely, and besides, it would be an honest mistake and one without much consequence. But data that's of any value is often much more complex and has real-world implications, like predicting the spread of an infectious disease, or assigning a person a credit score that can determine whether or not they're able to buy a house. Data is often subjective, and visualizations add yet another layer of subjectivity. First of all, it's not necessarily a given that you can even trust all data, even if it's in the format of video, photos, or audio, because they're becoming more and more easy to fake. The video on the left is a real video of former US President Obama, and the video on the right is a convincing computer-generated image. This video is already a few years old, and this technology is improving rapidly, making it easier and easier to fake realistic-looking images.
When you're giving a speech, make sure you use a lot of pauses and speak in a very weird timbre. Up and down and up, up, down, down.
As far as numerical data goes, 80% of statistics you find online are made up. That's not true at all. I just made that up. But it would really prove my point if it was true, wouldn't it? Sometimes people and corporations have points that they're hoping to make, and may be looking to find or to create data that confirms their desires, biases, and expectations. People often have ideas of what they want data to say, even before they find or collect it, and this can have an impact on the result. This is not how unbiased scientific research is meant to happen. A good scientist should gladly accept a finding that shows their hypothesis is not true. Even data that is true, in the sense that it doesn't have errors and is not fabricated, can be biased. One question to think about when analyzing the believability of data is who collected and sponsored the research, and what was the method? An obvious example of biased data is the claims made by cigarette companies in the 1930s and 1940s. These companies sponsored studies that found that smoking their brand of cigarettes was actually good for you. Diving deeper into some of these studies, there are some pretty obvious flaws in the methodologies. In this case, no scientists were involved, but rather the advertising company had sent a free carton of cigarettes to doctors and asked them if they thought they may be less irritating to sensitive and tender throats. Computer algorithms can be biased too. They are, after all, created by people, and each one of us carries unconscious biases that affect the way we think and the way we write code. Artificial intelligence technology uses machine learning algorithms to mimic the way humans think and learn. The danger of this is demonstrated by the findings of ProPublica, a civic technology organization. In 2016, they discovered that the mathematical models used by judges to help sentence criminals were coming to racially biased conclusions, even though it's illegal to use race to calculate such things. The mathematical models learned to use proxies for race, things like home address, which can indirectly determine race based on the racial segregation of certain neighborhoods. People from these neighborhoods were being illegally labeled as likely criminals, when people from white neighborhoods were less likely to be sentenced. This is an example of why you shouldn't blindly trust any old data you find online or in advertisements or computer algorithms. But what about scientists? Have you ever noticed that one day you'll read a headline that says scientists have found some kind of food causes cancer, and another day you'll find that they found the same food cures cancer? Like, is drinking wine supposed to be good or bad for you? Well, it turns out that according to one study or another, just about everything both causes and prevents cancer. This graph plots individual medical studies which show that a certain food protects against cancer on the left, or causes cancer on the right. The data is all over the place. The moral of this confusing story is that a single study isn't usually enough to prove anything. Scientists as a whole accept something as true only when a collection of multiple studies by many different scientists overwhelmingly agrees on a conclusion, though there will always be dissent. Scientists will be the first to tell you that they don't know everything, and there will always be future studies that disprove things we thought were true in the past. But that's not a reason to discount science. It's a good thing. Science is not a process of getting all the answers, but it's a process of reducing uncertainty. Clickbait journalists don't necessarily follow the same code, and they may not wait for scientific consensus before posting an eye-catching headline. Data believability is complicated even further by the fact that the same scientific result or data set can have multiple different interpretations. There are many different mathematical analyses that can be performed on a data set, some of which may produce statistically significant results, and some which may not. Depending on which one a scientist chooses to use may produce different results. A person or organization trying to sell a particular perspective may try 100 different tests, and choose to use the one that produces the desired outcome. This again signifies the importance of broader scientific consensus. Here's another interesting example of a data interpretation problem. Did you know that there's a 99% correlation between divorce rate in Maine and per capita consumption of margarine? Or number of people who died by becoming tangled in their bedsheets and revenue generated by skiing facilities? These are silly examples where it's obvious that the two data sets are either a coincidence or are caused by some third variable that's unaccounted for. There's a strong correlation between ice cream sales and drowning, but the hidden third variable is that both ice cream and drowning are simply more prevalent in summer months. Let's say that we have a data set that is unambiguous, unbiased, and factually correct. A visualization based on such a data set is sure to be true and unbiased, right? The way data is visualized, unsurprisingly, has an effect on the way that it's understood. You can visualize a perfectly legitimate data set in a way that shows the exact opposite of what the data is actually saying. This is a visualization of gun deaths in Florida that was made after a high-profile shooting. The y-axis is upside down, which makes it seem like gun deaths had decreased, when in fact they had increased. Was this visualization maliciously designed in order to lie to people? Or was it simply a poor design choice? The creator claims that it's the latter. But does it matter what the intent was if the effect is the same? It's incredibly easy to lie with data. So easy that it often happens on accident. You have to actively take steps to make sure that your data visualization is not misleading. It's very important that your visualization is vetted before you release it into the world. Having a scientist take a look at it and provide feedback is a critical part of the iterative design process. It may also be helpful to test it by showing it to someone in your target audience to see if they understand what the data and the visualization is showing. Sometimes, though, you may find that the best way to show something in an understandable way is to lie about it, and you simply need to figure out the most truthful way to tell that lie. That sounds a bit contradictory, doesn't it? Here's an example of what I mean. Our team spent months in conversation with a team of biophysicists to decide how best to show all these different interactions happening inside this energy harvesting organelle. An important piece of this story was to explain how these organelles capture and react to a single photon of light. The first challenge: how to represent a photon of sunlight. Photons are responsible for why we see. Therefore, they're literally something that can't be seen on their own. Furthermore, due to quantum mechanics, a photon is simultaneously a particle and a wave, with a wavelength that's larger than the object it's colliding with, for reasons outside the scope of this class. How do you show something like that? We went through several iterations. Any visualization of a photon is inevitably inaccurate, so there's no choice but to lie. We simply had to decide which lie is lying the least, and which lie is the easiest to understand. The issue of how to represent something when there are many different options, none of which are necessarily true, is something that comes up a lot in visualization. A simple example of this is that there is no true way to represent the world as a 2D map. A common projection from a 3D globe to a 2D image is an equirectangular projection. This creates nice straight lines for latitude and longitude that are equal distances apart, but it warps and exaggerates the sizes of land farther away from the equator. A projection like this one better shows the actual sizes of land, but it cuts up the map so that distances are hard to measure. There are many different map projections. Each one shows something well, at the expense of lying about something else. In a situation like this, when you do have to lie, it's important to let your audience know that what they're seeing isn't a true representation of a real-world phenomenon. In our research, we found that audiences tend to think that photorealistic or cinematic visualizations are actual photography. This is an argument for not necessarily making visualizations appear photorealistic. It's also an argument for properly labeling, captioning, or narrating your visualizations. It turns out that even if your underlying data is accurate and unbiased, and your resulting visualization is accurate and unbiased, the title or narration given to the visualization can still influence the perceived message of the visualization, with different viewers deriving opposing messages from the same imagery. There are many steps along the way of making a visualization where poor design decisions, conscious or unconscious biases, and errors can come into play to result in poor science communication and misinformation. People believe visualizations more than words. They're not necessarily right to do so, but this gives you, as a visualization designer, power that you have to yield responsibly. Fun fact! Deepfakes are videos created by artificial intelligence algorithms that synthesize human image and audio. Here's an example.
It's like, it was just, this was very truly surprising for me.